And so there were basically three things that popped out to me about this in terms of, and the first was when I looked at dt increasing. There was a handful, like several of you that see what's happening with the rate graph over here. So what's the whole point of taking the rate at the left side of an interval, and what we're saying, we're going to make it constant for that interval. So then what should we expect to see for our accumulation function if it's constant rate of change? What if it's a constant rate of change, what should we see as dt increases?
Proportional change in dv.
How about this? Is this what we should see? So I'm not sure if for those who submitted a file like this, if you notice that this is a big problem, right? The whole point of this is that we pick off a rate, and then for an interval we say, oh, we want that to be the constant rate for that interval. And then if that's the constant rate for that interval, what should the emerging accumulation graph look like? What should it look like? And why is this, what is incorrect about the way this is animating? So I think, Ashley, I saw you shake your head. What?
It should be like the same line the entire time, but it looks like the slope is changing.
Right. Yeah. So constant rate of change in accumulation is seen by the slope of the line, right? The slope of the line. And see how that slope is changing as dt increases. So it's like steeper, and now it's less steep. So that's kind of a major error, right? Because it's going against the whole principle of the whole principle of this, and that we have a changing rate function, but we're going to pick a rate to be constant, and we were going to accumulate at that constant rate according to dy equals mdx. And so if the animation isn't showing that, then that's kind of a major mistake. It is a major mistake. So that was the first thing. The other thing was the fact that like several of you made the same kind of strange mistake to get this kind of weird animation. I'm wondering about the kind of help that you're giving each other. I just want to kind of gently, caution you about how you can work together, and you can, but everyone needs to kind of do their own work. So there's a balance between, asking each other questions, working together, and making sure it's your own work and not somebody else's. So it just kind of raised that question in my mind. It's like, oh, this is kind of a weird thing. And then I saw it in other students, and then in other students. It's like, they all have the same weird thing. Why is that? Okay, so just gentle caution here that you should be doing your own work. Now, again, so what does good help look like? If another student comes to you with like a question, like, I'm kind of stuck with this, I don't know what to do. So what does good help look like? It's like, okay, how far have you gotten so far? Let's see what you've done so far. And then it's kind of like, can you ask some questions to get the person unstuck, rather than, well, here's what I did. Okay, so that's not good help, because the learning occurs when you figure it out, right? That's when the learning occurs, when you figure it out. So that we all want to have that experience. So helping another student is facilitating them figuring it out, not kind of sharing what you did. Okay, and I'm not sure that that's what happened, but it just kind of came to mind. Okay, so that's that. And then the next thing was, a lot of you put 3 for the starting y coordinate. So all 3 was just a place to put it. 3 has nothing to do with this scenario, right? The oil spilling into the ocean. This was just kind of a place we could always start the triangle. So 3 does not relate to the covariation of time and volume of oil spilled into the ocean, right? And so at any given t value, this is going to be different, right? It's going to be it's different value. So you don't want to use any 3s, okay? And also n's, right? So n has nothing to do with this context. N and 3. So n is just the vehicle that so there's another variable related to n that has to do with the context. That's what we should be talking about. So there shouldn't be any 3s and there shouldn't be any n's in your labeling of these points and distances. So that was the next thing. The last thing was, there was one more thing. Labels. Oh, so getting labels in the right place. So what I suggest is, and this goes back to a topic that we talked about like maybe a month ago or something, back in September, where it's doing something when you have all values can be somewhat not difficult, but then suddenly when there's variables involved, there's this shift and it becomes a challenge when maybe it shouldn't so much. And so we had that kind of discussion, like why does it get harder when things can vary versus being fixed? So and that was kind of illuminated by the location of these, and different students, they kind of would, as you would increase n, these labels would kind of fly off the triangle in different ways, okay? And so what I suggest is let's just make a triangle with values. So make a triangle with values. Say this is 1, 15, and this is 2, 15, and this is I don't know, 2, 19 or something. I don't know. All right, and so then find the location of where you want all these things to be. So where do you want to have that label for the ordered pair? Where do you want this label to be? Where do you want this label to be? Where do you want this label to be? And with the numbers, get them right. So if this is dt, if this is dv, whatever, ordered pair here, ordered pair where the 219 is, whatever. Okay, and then think about, okay, so how did I know to put it here? What was it about these values? What is that point relative to these values? And what is this point where I'm going to put that label relative to these values? And then when this thing is based on some variables and can move around based on based on dt, based on a, right? So this is actually a here. So now then you make the transfer to, having it with variables or having it with values that we can do maybe more easily, and then make this transfer to, okay, so now if a can change and dt can change and dv can change with it, all right, that's okay. We don't approach this any differently. And so then as that triangle grows, as you increase the n slider, then this dt should stay right in the middle on that segment, and this dv should stay right in the middle, right in that segment, etc. And then this ordered pair should stay the same relative distance away from that point as everything grows. Okay, does it make sense what I'm saying? So we want to get better. We want to get better at this, making the transition from, yeah, we could easily put these labels on if it was a fixed triangle and we knew the coordinates. Well, it's the same thing. It's just that your coordinates are based on some variables. So you're gonna do the same thing to locate those labels. Whatever you did to locate them with numbers, you do the same thing to locate them with variables. So then when your triangle emerges, these labels stay in the right place relative to the triangle. So I want everyone to thinking about those three things, making sure that you're not using 3 or n, so no 3 or n. Use only expressions, symbols, variables that relate to the oil context. And then if your file doesn't doesn't show this accumulating at a constant rate. You got to fix that. Okay. And so what do we want? So you want your constant rate to be with the rate at the left side. Whatever that rate is at the left side, that should be your constant rate for the whole interval. Rate correction. And then labels correction. And if you're struggling with the labels, then do what I said. So like just put a fixed triangle with values. Get the labels right for that triangle with fixed values, and then it's kind of really analyzing. Okay, how did I know to put it here? What exactly am I doing to put it here? What exactly am I doing to put it there based on these things? And then you do the same thing with the variables are there. Okay, any questions on that? Does that make sense? Okay, so since you have the, let's go ahead and do this one for Thursday, and then I'll give you some extra time on the sand unloading, the bigger one. Speaking of that, so with the sand unloading, a couple of you have submitted already. I haven't looked at it yet, but it's my experience that this is a kind of a really harder project, and so I guess I need to look at what you submitted, but that students are often coming to me for help on this, and that's kind of the intention. So I'm not sure how the files turned out, the two that submitted it, but I'm curious as to how it got done so quickly and without any help from me. So I just want to put that out there, but I am available for help, and that's kind of the intention of some of these harder projects, that you're going to grapple with it, and then you're going to most students are going to need to get help. Okay, any questions about these animations?
Do you want us to resubmit the oil one? Is that what you're saying?
Yeah, I'll put a new post because I think this is a really important one. It's really embodying like these core principles, and I want to see that you get it in the end, right? Even if it takes a second try. Okay.
So should we just resubmit it to like that actual oil?
No, I'll put another post up. Yeah, I'll put another post up. All right. Other questions? Okay. So did I say there'd be an assessment today? Okay. Well, there is, but you get to do it in pairs. Okay. And I'll give you we'll do a little prep work for it, but then you're going to work in groups on it. Okay. So here we go. Let's start by reviewing this assessment today is really about the accumulation function. So let's review that. Okay, I'm gonna have to close this up. All right. So the approximate accumulation function, it has this form, right? So this is the general form of it. And so please interject. I can't see your faces in order to, well, I can try here. Let's see how it goes. I might have to close up. But anyway, please interject and speak out if you have questions or comments about this. But this was the general form of the approximate accumulation function. And so it's primarily about two key principles, and these two key principles go back to like almost the very beginning of the course when we said like these are like the two key principles to maybe all of calculus, okay? And so the first one was change in dependent equals a constant rate times change in independent. So change in dependent equals the constant rate times the change in independent. And what do we know that better as?
dy equals mdx.
He wants dy equals mdx. The rest of you agree with that? Yeah, this is dy equals mdx, right? So where does that show up as the foundational principle in the approximate accumulation function that we worked hard on to develop, right? So what is the approximate accumulation function? It allows us to do what we originally did as a big piecewise function, but rather than having a piece for every individual interval, we could put it all in one line, right? That was the goal, to do all in one line, that accumulation function. So where do we see dy equals m dx in the approximate accumulation function? Where do we see that? So is there, how many of us is there? Oh, Angel made it, great, okay. So what do we think? Where do we see that showing up here?
The arcand of the approximate accumulation function, or the left side with the plus sign, you have your delta x, which is like your small, like those small intervals.
Okay.
Changes in the independent variable. The rate function, because we defined it so that it uses the constant rate that represents r of something is your constant rate of change. And we are accumulating a lot of those small changes. That gets you a lot of small changes in the.
Okay, so yeah, you're doing good. You're overachiever, right? So you're kind of talking about the whole function, and I'm just saying, where does this part of it, where does just the constant rate times a change in x gives us a little change in the dependent? Where does that show up? So that was included in what you said. So I think you were talking about this part here, right? Is that what you're talking about?
Yes.
Okay, so where do we see m dx? Where do we see that? Just in a nutshell.
Dx would represent either delta x or dx, and m would be the r of something.
Right. So, and what's the difference between r delta x and this r dx? What's the difference between those? Somebody else?
Delta x is the length of each interval, and dx is just the change in the last interval.
Okay, so what was the language we had for that? So what was the language we have for that to distinguish between these?
Delta x is the length of the completed interval.
Right, this was completed intervals, right?
And then dx is just the current one.
This is how far in the current interval, right? Okay, so we see it in both places, right? We see it as what? Accumulation in a completed interval, right? Change in dependent variables would be a little accumulation in a completed interval. And we have lots of those that we add up, right? And then we have some more little change in the dependent variable in the current interval as far as dx. So huge, right? I mean, it's totally foundational. Okay, next one, another important principle. Okay, so here we go. Yeah, I cannot get this thing to be out of my way. All right, there we go. I guess we'll do that. So yeah, so this is for every complete interval and within the current interval. There it is, okay? Next principle. Final value equals initial value plus change. Final value of dependent equals initial value dependent plus change. All right, how does this show up in the approximate accumulation function? Anybody have an idea? So this is kind of a hidden in plain sight kind of thing. How do we see this as, how can we see in this somewhere as final value equals initial value plus change?
Does it have something to do with the fact that we're using like the left side of the rate function, and you have that initial value and you're adding the length of the interval? Or multiplying by the length of the interval. Like how we figure out the upper sum of the summation notation. That's okay if my question didn't make
No,
sense.
I think it's a lot more kind of obvious and not so tricky as that. That seems like you're like trying to put it into a detail like this right here. You're saying?
Yeah.
No, it's a lot more of a big picture kind of thing. Anybody have an idea? Don't be afraid. If you had an idea, don't be afraid.
Does a of x represent the final value?
Okay, if a of x was the final value, then what? How is that final value seen as initial plus change?
Does that just mean like our completed intervals are our initial and like current is our change, I guess?
So like all the accumulation from the completed intervals, could that be thought of as some initial value to which we're adding a little more change? Can we think of it that way?
Yeah.
Yeah, it's good. Yeah, so y final equals y initial plus dy. And so we can think of the completed intervals as that's already been accumulated. So we can think of it as a lump sum, right? We can think of that's all the accumulation that's happened through completed intervals is like already happened, and then plus the amount that's accumulating in the current interval, plus the current change, right? Okay. So that's just a little overview of that. Let's take a look at the sand unloading graph because that's this is just to get us kind of prepped up for the assessment. I don't want to like send you into a cold. So here's that. Something else running. So slow. Okay, so what are we looking at here? So anybody, just tell me one thing that you see here. Explain, just describe one thing to me. We'll just kind of get our mind refreshed about what we're talking about.
Approximate rate of change.
Okay, tell me. So where do you see that? What is that? Where does that come from?
It's on the left graph.
The approximate.
Well, it's probably on both, but
wait, the approximate.
On the left one, it's the the blue steps that are being drawn.
So the approximate rate of change is the blue step function. Does everyone agree with that? Okay, where does that come from? Where does that function come from?
It's derived from the exact rate of change function indicated by the red curve.
Yeah, right. It comes from what we make delta x intervals, and we get these values of constant rates from the exact rate. And exactly how are we getting it from the exact rate function? Somebody else? So why is this step here and not up here or down here? So why does the step have this value for a rate?
Because we chose the leftmost value on the exact rate of change graph.
Right. So in each interval, you choose the leftmost rate from the exact graph and let that be the constant rate for the whole interval. Okay. Somebody else, tell me something else. Elizabeth, what else do you notice about this? What do you remember?
So like on the right side, we're like showing accumulation. So like the purple one is like our estimated accumulation based off of our approximate rate.
Good.
And the black is like the actual accumulation.
Good. And where does that purple, and is this purple graph, is it how do we characterize that purple graph? What kind of graph is it?
It's like approximate accumulation, but it's a linear piecewise.
Linear
of, like,
piecewise.
all of them added up together.
And where does that linear piecewise function come from?
So it would come from us estimating like the approximate rate functions times like each little individual step. So we're like adding them all up together.
Good. And what's the function rule for that, Ashley? What is it that we're graphing here?
We graph. So we take our is that like the summation part that you're talking about?
So the purple graph is just this part?
No, we take, like she was saying, we take the intervals from each approximate that we built, like the blue lines, and then you multiply it by the interval length,
Good.
and then we sum them up together to build like each step of the piecewise.
Okay. So actually, so from what you said, if we did that, we'd get another step function over here. That's what would happen. So what is it that makes it actual linear piecewise, like continuous, like this, with linear segments? There's a piece kind of missing that you didn't talk about.
We take, I guess, the derivative of the function.
So how is it that like in each interval we get it to, accumulate and increase in each interval and then kind of leave that behind rather than just actually having steps like completed interval, completed interval, completed interval?
They're lines, so I guess we're using like, I don't know, they're like slopes, so they're different lines that are all connected.
So it's this part. So if we didn't have this, if we didn't have the what is this part? What does this give us?
We're adding like what's from previous steps to combine them, I guess.
This is previous?
Sure. Left x minus left.
So what was
I guess
this?
that's your new, that you're added.
Right. This is the accumulation in the
Current interval.
current interval, right? It's that little extra amount in the current interval according to what, dx. Without this approximate accumulation function would itself be a step function, because you wouldn't be accumulating within each interval. You would just get the lump sum at the end of every current interval, and so you would just have a step function. And so it's the accumulation in the current interval that actually makes this into a linear piecewise. Does that make sense to everybody? Because if you only have what's from current completed intervals, then in the current interval you're not going to add anything on until the very end, and then you're just going to have a lump sum. And so then it's just going to end up being like steps. But because you include the accumulation in the current interval, then we get the linearly increasing accumulation through all the intervals. Okay, so what are the units? Somebody knew. So how about Angel? Can you tell me what the units are on all these axes?
On the accumulation one?
All of them. And take your pick, whatever you want.
I'll take the accumulation.
Okay.
So the vertical axis is going to be weight.
Weight. 100 pounds. So Y values represent this 3 represents what?
300 pounds.
300 pounds of weight accumulated, right? on the scale. Okay, keep going.
And then the horizontal axis would be time.
Time in seconds. All right. Somebody else. What about over here? Did Yasra make it? Is she here? No, Yasra?
She's not here.
Okay. What about this what about these axes over here? What are their units?
The one on the left, or the vertical one, is the rate of change of weight in 100 pounds per second.
That's right. Those values are 100 pounds per second. And these?
And the horizontal one is the same as for the other graph. It's time in seconds.
Right. Okay.